So I really appreciate everyone joining us today to talk about data-centric security. It's one of our favorite topics here at Fluree. It's something that we take very seriously. It's core in our product. And we're going to talk about a number of things. In fact, what we will cover is explicitly what we mean when we say data-centric security. So there's probably a lot of things that people infer when they hear that term, but concretely, what are we talking about? Secondly, why we should be thinking about data-centric security, why we view this as an important characteristic as we go about data management. And third, how Fluree implements data-centric security. So we're actually going to go through the details of the questions we most commonly get, which is, okay, I get that you say you do all these things, but how do you do it? Fundamentally, how is it done? How does this work in Fluree? And we'll cover both concepts about how we handle our append-only log structure of how we're doing data storage at the core level. And we'll talk quite a bit about SmartFunctions as well. So let's start out by answering the first question. What do we mean when we say data-centric security? And we use this term a lot. It's really synonymous with what we mean. It's this idea that data should be able to defend itself. And it's all about, we think, a broader trend of security in general moving into the infrastructure layer. So we've always tried to do security at the perimeter layer, whether that's firewalls, whether that's VPNs, et cetera. And of course, as the cost and implications of security are going up and up, and people are getting through these outer layers, what we're seeing is a broad trend, whether it's in computing hardware or in Fluree's case, in data, of moving that security to the infrastructure level. It offers greater protection, and we'll show it actually offers a lot of additional value to your data. And that's really what Fluree is all about doing at the end of the day. It's bringing you additional value to the information that you have. And we do that in several ways. One of the core tenets of this is going to be security. So when we say data defending itself, what do we mean? We mean that you can retrieve or access data, whether you query for data or however you get access to it, and you can independently know that you can trust that data, that there is no way that that data could have ever been manipulated. There's no way that someone could have implied that data was there that really wasn't, or faked who put that data in there. So this all gets to the provenance of information. And if you think about it, what we have today with a typical database and any typical application you use, whether it's a financial application or a CRM application, is that you end up seeing data on the screen, but you just have to take a leap of faith that that data has integrity, that someone hasn't manipulated it, that it really is the data that whoever said they put in there. But we don't know, and the implications of not knowing and the stakes of not knowing are starting to get higher and higher as we're venturing into new types of applications where this becomes critical. And we'll talk about that. Secondly, knowing that you can reproduce the data. So if I can look at data, even if I can prove the provenance or how it got there or that it wasn't manipulated, if that data could just disappear tomorrow, did it do me a whole lot of good? And so this comes into a lot of problems in computing. We address this through our ledger capability and through the database query capability and a feature we call time travel, which allows you to issue any query at any point in time. But importantly, you can reproduce the state of the information at any moment in time. And again, a typical database has really been designed to make it easy on purpose to destroy data. You know, when you update a field or a piece of information, it quite literally destroys the data that used to be there. I mean, it might exist in a log file for a while, but there's no easy way of getting back to that information. And so Fluree approaches this where data itself is never actually destroyed. There's a couple caveats, a couple sort of release levers for emergencies that can be in place if that is a critical requirement of yours, maybe under a Consumer Privacy Act law or something like that, where you have a legal requirement to destroy information. So there are certain circumstances in which it is possible to do something like that. But in general, all data is reproducible and provable. And then the third point here, when we say data defending itself, it means that there is no way to circumvent security. And that applies to both data updates, who's allowed to update what information when and under what circumstances, but also queries. When people are requesting data, whether it's an application requesting data on behalf of an end user, or whether that's a machine integration that's requesting data, they should never be able to get around the security of the data itself, and that's important. And what this means is effectively, if you have a system that is that can defend itself, that is housing data, it means that this doesn't necessarily have to sit behind layers of firewalls. Because if you don't have a contract in the rights to see information within that data repository, you'll never see it. And the way we accomplish this today is we build APIs, we build security into an application tier, we do all these layers and things. But fundamentally, we do these things as workarounds because our data repositories don't have a native capability of defending themselves. As soon as we introduce that capability, we can now start to broaden people having access to data. So why is this important? And we contrast these two views of thought, and one is around an application-centric approach, and the other is what we refer and what we're designed around, which is a data-centric approach. And over the last 40 or so years, we have been building applications mainly focused on automating processes, shuffling forms between people. And the architectures that we use and the database we use and the technology we use are all based on decisions and constraints to design those types of apps. The data within those apps was never what derived that much value for us. It was always the fact that it automated a process. It made a process more efficient. Now, of course, over the recent years, and increasingly so, we're getting into a situation where the data itself holds as much, if not more value than the process automation. But we're kind of sitting on this architecture that was designed for a different world. So we end up with all of these siloed applications. Many of them are storing the same data, just duplicated, which is difficult to maintain. And if I want to access data across these siloed applications, I have to turn to yet another workaround, which would be something like a data lake or a data warehouse to try and aggregate them together. It's important that all these data repositories have no security natively within them. The security is sitting up above. It's custom coded into these APIs. It's custom coded into the app servers themselves. So when we suck data out from the back end and put it all into a data lake, we have taken effectively any security this data had and stripped it out. And this is also where we're starting to see some pretty significant data breaches. A lot of the more prominent ones over the recent years were because people aggregated a bunch of data, pulled it out of its native secure environment, put it into something like a data lake, and then accidentally left the server too exposed or something like that. So when we start moving data out, and because we can't easily get our access to it, we end up creating inadvertently other security issues. And we think we're quickly moving to the world where we have more and more applications that should be data-centric. So kind of this view on the right. And these data-centric applications should have pods of information, but be able to seamlessly connect to other pods. And increasingly, we have many applications that need access to a single set of data. So in the world on the left, we only ever had one application that was married to a single database. But now we have data that has a lot of applications that require information to it. And part of our issue in dealing with that problem is that we end up building in the data security, and we have to do it over and over and over again in every single application. Because again, the repository itself has no way of enforcing security on its own. And hopefully we build those all out the best way and the right way possible. And also in this data-centric world, we should be able to connect information together so we don't have to duplicate data. And we'll talk briefly about a set of standards that exist that Fluree is built on top of that enables these things to happen. It enables data to seamlessly integrate with other data without having to build hard code APIs, without having to build ETL processes to transform data back and forth. And it's sort of the environment that is going to unlock the potential we have with data going forward. So that's one reason. We sort of have a different view on the value of data and why data defending itself is important. The other is cost. So this can be a huge benefit. And this is a cost estimate here of an application that is what we would consider data-centric, an application that other people need access to the data that's being stored. So not an application that has a database that's only serving the single app. And using some averages and the stats here from different sources on costs are below, but a typical application, enterprise application today, costs about $175,000 to fully build, and that's building the app, the testing, and everything around it. That's the green bar here. That's what it costs me to actually get the functionality I need. Everything we see in the blue bar are costs that get added on when we're trying to make the application data-centric. And it's mostly because we have to share data. Other customers, partners, other apps internally need access to that data. So we have to turn to things like APIs. APIs cost an immense amount of money to build and maintain. And importantly, they are becoming the highest vulnerability from a security standpoint within the enterprise today. There's a really nice paper that just came out from Akamai that said now that 73% of all corporate hacking attempts happen at the API layer. But we have to pay money to build this custom API, and then we have to maintain it. And the more APIs we have, obviously the more cost that comes in. And the tragedy of all these custom APIs isn't even just our own cost. It's that we actually push additional costs now onto our customers, the people who need to interface with our custom APIs. Because now they have to write custom code. They have to maintain that custom code over time as it changes. So the cost of APIs for data sharing really explodes the cost of a typical app. But if we had this data-centric app that had these characteristics and the data platform itself had the ability to natively, insecurely share data without APIs, then all of these workarounds that we're implementing and spending on top of the core app would never have to be in place. The app could just cost $175,000, but still have all the capabilities we list here, and we avoid the security vulnerabilities at the same time. So cost is an important reason to think about data defending itself and data-centric security, again, for these class of applications that we call data-centric, where data needs to be shared out with other consumers. And the last reason to think about data-centric security is because we want to participate in this new ecosystem, because it's going to be required for us to do so, to take advantage of newer technologies. And so Fluree sits on top of semantic web standards. So the World Wide Web Consortium standards of semantic web. And what it does is it effectively takes the web as we know it today, and instead of being a web of documents, which is how we interact with the internet and the web, it becomes a web of data. And that data, again, is interoperable. It doesn't require custom integrations to be able to merge and combine it. And when we think about companies and even reaching through supply chains to not only my supplier, but my supplier's manufacturer, and assuming I have access to data, being able to pull information all the way through and have the insight through my partners, or aggregating data together across my applications without duplicating it in every single application. All of these things are a web of data. We have a whole new generation of technologies that are going to require this type of interoperability. Digital assistants is a good example of that. If I ask Alexa or whatever the case may be, or the new business version of this to go do something on my behalf, If it does not have the ability to go out and figure out where the information is, what needs to be manipulated to do that on your behalf, it cannot be successful. We will be relegated for a digital assistant to having to hard code, which is basically what's happening now, hard code every single action that it can take and basically build against custom APIs to do so. If we really want to take advantage of this type of technology, we need the ability for it to be able to go out and discover things and do things on our behalf without someone not having to anticipate everything we want a digital assistant to do and hard code that. Or things like smart cities. You know, how are cars going to talk with other cars, especially if they're built by other manufacturers, or talk with the stoplights or other traffic data in cities that are also built by different manufacturers. If we adhere to these standards, we can create a web of data that, regardless of the manufacturer, there's an ability to combine information. And the semantic web standards, which were, started to set in stone, World Wide Web Consortium organizes them. They were originally conceived by Tim Berners-Lee, who invented the World Wide Web as we know it as well. Another key aspect of being able to more strategically leverage data, especially across different apps and even through partners or across partners, is that data is becoming the fourth pillar of differentiation. So we've always looked at differentiation of business being people, processes, and technology, the three pillars. And if a business can outperform their competitors in those pillars, they can effectively be more successful. We see data now becoming that fourth pillar. So the most successful companies are going to be the ones who can most strategically leverage data for differentiation. And we need a web of data and some of these concepts in place to be able to more strategically leverage that data. And of course, lastly, the business impact of security is increasing. The cost of data breaches are hitting businesses harder and harder, the more frequent and the more severe that they end up happening. And they're happening more commonly because, again, we're building and we have hundreds, if not thousands, of APIs sitting out there. It's difficult to keep them all maintained. It's difficult to watch security around them. And again, Fluree's answer would be, well, if we can secure data at the source, then we don't need to worry about embedding security in things like an API layer. Inherently, that security is present. So let's talk a little bit about how we approach data-centric security. And when we think about these data services, these nodes of data that are sitting out there, we think about them in layers. And this is what we refer to as the Fluree data stack. Because it's not just a database, it's actually the business rules and security and the cryptographic components that allow you to independently verify integrity of data that sit within the stack. It's things that today you would have to pair a typical database up with a lot of code in an application server to achieve. Here we're bundling that all in a single data platform. And at the core of that platform, the center circle, is this concept of trust. This idea that every piece of information in there needs to be effectively in a vault where all the data can be proven. If anyone were ever able to tamper with the data, it should be detectable that that data was tampered with. And we should be able to prove the provenance of every piece of information we have. We should know exactly who put that data in there, when they put it in there, what was changed when that data changed. And right now, we just do not have that level of traceability around information. So at the center here, it's trust. We wrap trust with semantics. Semantics are based on these World Wide Web consortiums. Fluree at its core uses RDF. We'll spend some time talking about RDF because it's important to this is the underlying data format that Fluree uses to build the security in. So as we describe how we do this, we're actually going to be taking a look at RDF data and how Fluree uses this. But this World Wide Web Consortium set of semantic web standards for which RDF is in, for which the SPAROL query language is in, a whole set of standards fall under this umbrella. This is what gives us the ability to have concepts of global and shared schemas that can interoperate with other sources of data and allows us to effectively combine data together, linked data across data sources. The next layer is security. So this is where, which we'll talk about here, our smart functions come in. And smart functions are simply code as data that get triggered based on patterns and information that end up restricting the amount of information that individual users have the ability to see. So if you request data from a Fluree instance, unless you have a contract, some sort of authority to do something with that, you will never get any results back. And then depending on these smart functions, they will end up dynamically filtering out data. And what this ends up doing is allows you to request whatever data you want, but you have effectively a different version of the database than another user with maybe slightly different security or a slightly different view in the information. So smart functions is where we control this security layer. And then we have time. So time is important for the reproducibility of the information. And especially if we think about this web of data, if we're issuing queries that can actually get information from multiple data sources and bring them together as though they're part of the same database, if we can't lock in time, we cannot have reproducibility. So it becomes very important for us to be able to understand the concept of time. Again, a typical database has a notion of only one time, which is whatever the latest update was. It doesn't have a notion of what it was a second ago or a minute ago or a day or a year ago. At its core, Fluree has this concept, and you can issue any query and instantly get a response for any moment in time. And then the last layer here is data sharing. So again, we're focused on these data-centric apps. The data holds immense value. It means that people want access to that data. They need access to that data, whether that's your customers, your partners, or other systems internal to your organization. So we think a data repository should natively have the ability to share data directly. And we do this through several standards, the SPAROL query language, which anyone, assuming they have a contract with the data set, is able to issue a query for anything they want. Again, the data will be filtered out based on what they have the ability to see. Fluree QL, which is a JSON version of basically SPAROL with some other capabilities in there. And then we also support GraphQL. GraphQL is quite a bit more limited, but it is one of the most rapidly adopted technologies in the recent years. So there's so many developers that are using GraphQL. There's an immense amount of open source tools that can natively talk to GraphQL. And the neat thing is you can use one of those tools that can talk directly to a Fluree data stack, a repository. As long as you're asking for data, even if it's permission, you don't even need an application server. So a front end like React web app can just request data via GraphQL and paint it back. And each user might see different data because they have different permissions. But the role of the app server as it relates to specifically filtering out or controlling permissions around data disappears because the data can defend itself. So these are sort of the layers we look at for securing data. So the first kind of piece that we're going to talk about is this concept of trust. And there's two main components that we're going to focus on for the rest of this presentation. How do we build this cryptographic trust into the data? How do we know that data hasn't been tampered with? How do we know who put data in there? And this all comes down to how we fundamentally store data. And as I mentioned a couple times, we store data as an append-only log in a format called RDF. And RDF is, again, a World Wide Web consortium for data. So let's do just a really quick RDF primer, because I think it's helpful as we kind of build up how we treat this data and secure this data, that we have a basic understanding of RDF. RDF and databases that deal with RDF are sometimes called triple stores. And that's because RDF as itself has 3 pieces of information in it. And this is a very, very simple set of RDF data. And these are effectively what the lines in the log file look like as Fluree is writing new data and new updates into the system. So RDF has 3 parts. The first is what we call the subject. It's the object or the item that we're dealing with. And you see here, this has 3 subjects. In particular, this subject here of Bob has a bunch of information about it. The second part is what we call predicate. It's effectively the property. If you thought about a relational database, this would be the column name. So Bob is a person. The nice thing about RDF is that you can express any conceivable piece of information in the RDF format, and it's immensely flexible. You can take RDF and you can represent it as a relational database. You can represent it as a document database. Its most power comes from representing it as a graph database. So we see a bunch of facts about Bob. Bob's a person. Bob is a friend of Alice. Bob was born on this date in 1990. Bob's interested in the Mona Lisa. Bob has an identity, a digital signature, if you will, that can uniquely identify them. And then here's some information about the Mona Lisa. It was created by Leonardo da Vinci. So this simple format of data in a log format actually creates this graph down here. So here we see Bob. Bob was born on. Bob's a friend of Alice. Bob's interested in the Mona Lisa. The Mona Lisa was created by Leonardo da Vinci. So I hope you can see that this flat file data here actually represents this rich graph of data. And the really neat thing about these semantic web standards is that all of this data doesn't have to be in the same database for it to all be connected as though it is. So in fact, everything we see here in the green could be sitting in a different database that's just maintaining, in this case, you know, information about art and artists and related items. A good example of something that might do this is Wikipedia. So Wikipedia is entirely based on the RDF standards. We're seeing more and more technologies like the FHIR standard in healthcare for universally representing healthcare data is leveraging the same set of semantic web standards. We're seeing the research community start to leverage for interoperability amongst research data sets, these same sets of standards. And importantly, because it allows you to represent this data in this very rich way and connect data that doesn't fundamentally have to be together. So this is just a quick overview of RDF and what it looks like. And again, Fluree at its core is storing at the ledger level RDF data. So when you talk about RDF, the next thing you need to talk about is how do you query data? And the standard that goes along with RDF is the SPAROL query language. It is the standard for graph database query languages. So the neat thing about SPAROL is it's really easy to understand because it actually is just a pattern match against the RDF data. So once you kind of get the basics of SPAROL, it's really easy to do a lot of very powerful things. It's important to review SPAROL a little bit here because when we get into SmartFunctions, it is going to leverage these same concepts as an option. So if I want to do a query and say this was all the data in my database and I wanted to say find all the friends of Alice, what I can do is say, well, I want to see a friend of Alice, which we'll see as a direct match right here. So a friend of Alice. And here I use a question mark, which means I don't know who, just find me every matching pattern. In this case, there's only one matching pattern. This piece of RDF here, Bob is a friend of Alice. So Bob goes into this variable and that's the variable I'm selecting out. So if I executed this query against this set of RDF data, I would end up seeing Bob. If I wanted to do something like, say, find all the friends of Alice who are interested in the Mona Lisa, I can just start adding statements to my query. So the first statement is identical, right? I want to find friends who are a friend of Alice, but then this friend must also match the next statement, which means the friend must also be interested in the Mona Lisa. And I see up above in the data set, I have that match. So here Bob is a friend of Alice. And here Bob is interested in the Mona Lisa. So I would still see Bob. If Bob wasn't interested in the Mona Lisa, I wouldn't see him. If there were other people, like if I had Alice's data in here and she was interested in the Mona Lisa, I would see Bob and Alice, all the matches to that statement. But you can really just start crawling the graph, and it's crawling the graph that allows us to do really powerful but simply stated permissions. And we'll extend this concept just one more level here. which is let's find all the friends of Alice who are interested in any artwork by Leonardo da Vinci. It doesn't have to be the Mona Lisa. So again, we started this out the same. We'll find friends of Alice and friends who are interested in a piece of artwork, but in this time we haven't stipulated that the artwork has to be the Mona Lisa. We're just saying any artwork. But for any artwork, that artwork has to be created by Leonardo da Vinci. And this simple query would find you anybody who is friends with Alice, who's interested in any artwork by Leonardo da Vinci. It doesn't necessarily have to be the Mona Lisa. So this is very basic SPARQL, but it's really easy to understand, and especially because the statements in SPARQL really match up with how the data is stored. So it's very powerful, but you can get into analytical queries, you can get into combining graphs together. There's an immense amount of powerful capabilities within the SPARQL query language. But this is how you find information. This is how you understand if relationships are sitting in the data. So we've done just a quick primer on RDF and a quick primer on SPARQL. So this doesn't yet answer how we secure the data. So let's start getting more specific into how we know data has integrity and that it hasn't been tampered with, and then subsequently how we start to build rules around the security about who can do what with the information. So we'll start out with the first one. Now again, Fluree stores data in an RDF format. So this is the same set of data that we've seen, but I mentioned it's an append-only log, and of course data is changing over time. So what we see simply here is the original set of data that we started out with, and we're at a moment in time where that data exists. It's what is in the database, but now someone updates the database. And say Bob had a falling out with Alice and is no longer a friend of Alice, but has also now befriended Jane. So Bob's now a friend of Jane. I don't have to reproduce the whole database. I just have to represent the simple changes that happen to the data up above. So I will have a new moment in time after I complete that addition. But all we're doing in the sense of Fluree is we're appending these new facts to the log. And this log can never be changed. And we'll add some additional pieces to this so we see how that cannot be changed in practice. So RDF doesn't really, at its core, understand time. So here we struck out that Bob's a friend of Alice because he's no longer a friend of Alice, but we don't have a real good way of representing that in RDF. And this is where we get to a couple simple extensions to RDF to do the magic that Fluree does with data and data provenance. So if we add just another piece of information to our RDF, true and false, we're able to start representing this. So true means we have a new fact. This is true, it's a valid piece of information. False means we're retracting a piece of information. So here we still have our time one data up here, but now in time two, what we're doing is saying Bob is a friend of Alice, which used to be true up here, but now we're saying it's false. It's no longer true. But we're now asserting that Bob is a friend of Jane. So this information is true. So if I basically played this log forward and retracted the information as I see it, I now have a new set of data as of time two. So here's my data as of time one, this block up above. But now if I play this forward, I have a new set of RDF as of time two. And you see here the change here. Bob is a friend of Jane, and of course, Bob is a friend of Alice, no longer exists in the data. So that's a simple way of extending RDF a little bit to allow us to understand concepts around time and be able to play and reproduce data. But we still don't have what we need in here to prove that this data has never been tampered with or prove how these pieces of information got in there. And for that, we need to add just one more thing. And what we add is for every piece of information, we add a reference to the transaction that put that data in there. And this way, when we're querying or looking for data, we always get this complete piece of information. Even if I'm just looking for, everyone that was born on the 4th of July in 1990, what the underlying engine is doing is it's returning all of these rows, all these pieces of RDF that satisfy that. So they have this additional metadata, which is a reference to the moment in time that piece of data actually got into the system. And another thing we can do is that this transaction can itself become its own set of queryable data. And that's what we've done here. So this was put in here as a reference to transaction 1, but here's now transaction 1, which has itself become a subject. And it has additional metadata about it. And the neat thing with Fluree is there's certain pieces of data that we always store in the transactional metadata when a transaction happens. And this allows us to get the provenance data. But you can extend this. So if you had additional metadata about the transaction, say you wanted to include the IP address that a system picked up as someone attempted to update that, you could include that. You can expand the data that is sitting in this transactional metadata. But it allows us to get from any piece of RDF to the transaction that put it in there, and then the transaction data itself is queryable data, and I can find out whatever I want about the transaction. This is how we prove the data hasn't been tampered with. So we include a cryptographic hash that represents the updates to the data, this RDF that came within this transaction. That also get combined with the previous hash of the previous moment in time, and this effectively creates a blockchain. Except instead of each row in the blockchain representing, say, a Bitcoin transaction, each row in the transaction is representing a very flexible piece of data that can be turned into a graph database. We also store the signature that put the data in there, and we're able to trace that back, and anybody using the cryptographic proofs, the math, can trace the signature back to an identity of who actually put this information in there. So here we have cryptographic proof that Bob put this data in here. No one else could have done it. Anyone can independently verify not only that this data hasn't been manipulated from the hash, but by looking at the cryptographic signature, it'll point to an identity. We know that identity is associated with Bob. We know there's no other way this data could have gotten in there except for Bob. And again, anybody can prove this out independently. This is using standard cryptographic techniques. You don't need Fluree, or you don't need to trust Fluree to be able to validate that information. And then we'll also record the wall clock time that this happened. And this allows us to do some nice things with our time travel. Instead of saying, I want to look at time 1 or time 2 or time 3, which is every time we change the database, we can do things, say, I want to see the data or issue this query as of, May 1st, 2020. And of course, this time is down to the millisecond. So this is how we put the pieces together. We have not only this append-only log structure, we have transactional metadata that can point every piece of information, every datum that exists back to the transaction that put it in there. We have all this metadata about the transaction, including some of the cryptographic components that allow us to prove this data has integrity. And we're simply building this information up over time. Now, of course, when we're issuing queries to Fluree, we're not reading and replaying this whole log file. That would be terribly inefficient. So we create, like most databases would, indexes that allow us to answer questions or queries incredibly quickly. In fact, typically sub-millisecond, most queries would respond in. So those indexes are leveraged, but at the core, if we ever want to back up or have the integrity of the core data, all we need is this log file. Because with this log file, we can reproduce any moment in time and all the proofs we need to do it with. The other really nice thing about RDF in this format is that as changes are happening and we have new moments in time, effectively, this is an event stream of our data changes. So it becomes really easy for listeners to kind of watch for data changes. Maybe I want to see every time a new email address is added to the system, because if one is added to the system, I want to kick off a welcome email to somebody. Trivial to do in a system like this. All you need to do is listen for changes. All you want to do is look for the property of email address. Maybe you just want to know new ones, so you want to make sure that value is true. You're not looking for any time someone's deleting an email, only the brand new ones that are put in there. And then that kicks off a process. So there's a lot of powerful things you can do when you have this flexible data format and you have effectively a data stream of changes coming through. And while it's outside the scope of what we're talking about today, we do some really cool stuff with like React front ends where we build automatic real-time front ends, because effectively we're embedding a Fluree graph database. We have a version of it in JavaScript. We're embedding it directly into the web browser. And these changes, the stream of changes are coming across the wire, and then React's automatically able to tell which UI components a user's looking at that might have updated, and it automatically will change things. So building apps on top of this data structure can be done very efficiently and really easily. So there's a lot of neat things that this starts to expose for us. So that's how we secure the data at its core. There's another component about data-centric security we talked about, which deals with permissions. And for that, we turn to SmartFunctions. And we'll show a couple of examples here. So for a SmartFunction is a set of code. The code is actually stored as data in the database itself. So the SmartFunction is itself just RDF data in the system. So it has the same proofs, the same integrity as everything else, but it's in a special location that Fluree understands to look for it. And based on it being in the system, it will use it to enforce the security of the data that we want to express. So a SmartFunction just sitting in the system does nothing by itself. So it's just code as data. It gets triggered, and it gets triggered based on a number of things. And right here are the core things that can trigger a SmartFunction to run. A SmartFunction can be attached to a collection or a class or a type, whatever sort of terminology you want to use. So like a person. So if you thought about this in relational database terms, maybe you'd have a table of a person table. And basically you're saying, trigger this SmartFunction that's going to perform some logic anytime anyone tries to manipulate that person table. So it's pretty high level at that point. It's not very granular. It can also be tied to a specific predicate or property. So, you know, in our RDF example, we had a friend of. So a SmartFunction might get triggered based on someone trying to change a friend of. A SmartFunction will get triggered based on the type of request it is, whether I'm trying to update data or whether I'm trying to access or query for data. There may be different sets of permission for each. And the user itself is part of the component of what triggers a SmartFunction. So people do create SmartFunctions that actually just enforce the shape of data. It makes sure, for example, if you're adding a person, there always has to be a given name and a last name. This can just help with data integrity in general. So SmartFunctions can be used for capabilities like that. Just making sure that all the data that gets in the system is clean and adheres to all the rules that you want it to adhere to. But of course, it can be used when tied to the user issuing the request, whether it's an update or a query, to what needs to happen. The SmartFunction has a lot at its disposal to answer these questions. Can the user see this piece of information? Or can the user update this piece of information? It can use the entire graph database. So it can look for relationships in the data and see if they exist. And this allows basically permissions to effectively auto-update themselves based on information in the system itself. If you wanted a SmartFunction that said the only people who can see an employee's salary are the employee or the manager or the manager's manager all the way up the chain, that's a simple SmartFunction that you can express. And anyone asking for salary simply won't see that data if they're not part of that rule set that exists. But as soon as that manager is disassociated from that employee, they instantaneously lose the ability to see that employee's access. So the data itself is controlling a lot of the security around who can see what and under what conditions. It can also use the identity of the user issuing the request, and this is how we determine who's asking for what. It can look at the data that's attempting to be modified. So in the case of a transaction, we can hand the SmartFunction, here's the set of data that this person's trying to manipulate. And then comparisons can be done against that. Maybe there's a business rule that says we have a contract and contractually we cannot raise the price of a product by more than 5% a year. Well, we can look at the data the new price that someone's trying to update in the database, and we can actually query the database for that product's price 1 year ago. We can use time travel, and then we can do a simple mathematical comparison, make sure it's not more than 5%. As long as it's not, we allow the change. If it is more than 5%, we'll effectively disallow the change. So you can actually codify things like contractual rules because you have the information to be able to make those decisions. And we'll quickly show a couple examples of a smart function. I would love to point you to Fluree's YouTube channel. There's a great video that Lillian, one of our senior engineers, did there on SmartFunctions, where she actually codes through an example. There's sample code. It's a great voting application that deals even with decentralization, this idea of multiple parties sharing a common database, but being able to validate and sort of check on each other, in each party having concepts of voting and putting in rules as far as when transactions are allowed based on voting. So there's a lot of very advanced concepts that you can do with smart functions. We're just going to use our simple data set that we started out with and create a couple simple smart functions just to illustrate the concepts. So here's our data set that we started out with, our RDF data. Here it is represented as a graph up here at the top. And this is an example of a smart function we might want to put in that says a user can only update their own friends. Meaning that if I'm Bob, I'm the only one who can say, I'm a friend of Alice. Alice isn't able to say that I'm a friend of someone else. It's a very simple rule, but it leverages, again, the data in the database, and it's automatically enforced for all the users. So we're just representing this rule in a JSON-like format here, but we're gonna say this applies to transactions or updates, and this gets triggered anytime someone's trying to manipulate a person. So remember, Bob is a person, and only when they're trying to modify is a friend of. So here's the Bob is a friend of Alice. And the actual function, the code that is going to execute, is using one of our very nice and flexible built-in functions. You can write your own functions, even call your own functions, reusable functions within Fluree. Relationship is a built-in one. And all it does is say, returns true or false if a relationship exists. And we have a couple special variables in here. One is the auth, the identity of the user who tried to transact. And again, we have cryptographic signatures that allow us to determine that and prove that out. And we want to follow that auth points to an identity and points to the user that is trying to be updated, the subject, which is this part. And this one simple rule basically says that Bob's the only one who can update Bob's friends. No one else in the system can update Bob's friends. And if anyone ever tries to, it would reject that capability. Very simple rule, but very powerful, would apply to everybody. Let's do something a little bit more complicated or a little bit more involved. I guess no more complicated, but we're going to expand the rule just to give you a sense of using the same relationship function. Here we're going to look at queries. And what we want to do is say, for some reason, even though I'm connected to friends, the only people who are my true friends are people who like art by Leonardo da Vinci. And therefore, even if someone is a friend, if they don't like art by Leonardo da Vinci, I don't even want to know they exist. Effectively, that data disappears. It doesn't exist for me. And this would be an example of a smart function that could enforce that particular rule. So here we're going to use the same relationship. We're going to start out with the identity of who's issuing this query or request. And we're going to follow these chains. So we're first going to say the identity of the person. So say it was Bob. So we're here. Has to be a friend of whoever we're trying to view, the subject. So say we're Alice, or Bob may have Jane or other friends as well. So it would apply to each of them individually. And that friend must be interested in any artwork. We're not defining it here, but we're saying that artwork must be created by Leonardo da Vinci. And so from the identity of the individual, we're following this chain and making sure that we end up with Leonardo da Vinci over here. And if for some reason that chain does not exist, the data effectively disappears. It does not exist for me in the system. It is filtered out. And using a rule like this allows every single individual user to effectively have their own custom database, which is what allows us to do the type of work we do without having to build custom queries or custom APIs, because custom APIs would have to modify queries to enforce this data security. Here we can now allow users to just issue GraphQL, issue a query for whatever you want. If you don't have permission to see it, you just simply won't see it. So it allows a lot more flexibility. So I'll wrap up there, and I think there might be a couple questions. If you have any, feel free to put them into the Q&A section. Just some of the key capabilities of Fluree. We talked about the immutability. We talked about SmartFunctions. We talked a little bit about semantic graph. There's a lot more there to cover. We didn't get too much into time travel. Decentralization we didn't really talk about, and some of this real-time data stream capabilities, not as well. So those are all broader topics. Encourage anyone to go and use Fluree, download it. You can download it for free on our website. We've got lots of videos, tutorials that talk about a lot of these different concepts. So we would love to have you try it out. And I will jump into and look at a couple questions. So the first question is, given data security is only as good as your ability to identify, authenticate, and authorize your users, is Fluree integrating with other identity providers and or standards? And the answer is yes. Most of our customers have concepts like that. There's sort of this epitome of security that's practical anyway today, which is public-private key cryptography. And the reason that that's so beneficial, or at least one of the reasons, is because you actually can prove you are who you are without ever divulging your private key, effectively like your password. So you can log into websites, but you never have to give a website your password. Another interesting thing, especially when you think about these concepts of the semantic web or multiple data repositories, that I can independently prove to each data repository I am who I am without each of them having effectively storing my password. So I don't ever have to worry about anyone storing my password. At its core, this is the type of identity that Fluree uses. It's public-private key cryptography. So if I want to use other forms of identity, we have other options. So a lot of people, you know, maybe their users aren't used to using that sort of identity. Maybe they want to use OAuth because they have Google accounts centrally. All of that is fine. All of that is possible. There's several different options. By taking these options, technically you bring down the ultimate security level just a tiny bit, but as long as they're implemented well, they can be as, if not more secure than a typical application would be today. That's usually handled via a simple proxy service, and that's how most of our customers end up handling that. So effectively, a proxy will receive the credentials, say the OAuth credentials, and will then turn around and effectively issue that query as the user based on it knowing or having the integrity or trust or whatever level of capability you want that that user is who they are. So I have another question here, one about our RDF store. And I'll point out that our RDF store, Fluree is itself an RDF store. So Fluree is a semantic graph database. The second part of this question is about blockchain and blockchain's role. So we've actually gone through most of the core components of blockchain. We actually probably didn't talk about consensus. That would be the only thing we left out. But when we went through and we talked about cryptographic signatures and hashes and how we tie those hashes together to prove the integrity of data, that is the technology that encapsulates blockchain. There's one additional kind of main component to blockchain, which is consensus. And Fluree supports a couple consensus mechanisms if you choose to run Fluree in a decentralized manner. You do not have to. And I would say most of our customers just run it like a graph database for whatever they're building, but a graph database that has, you know, if you will, some of these superpowers to it. There's a question about why React and not things like Angular or Vue. And I'll only point out that we have a database, the graph database, that's actually entirely in JavaScript that can be embedded directly in the browser. And it weighs in about 180 kilobytes compressed, so about the size of an image that you would put inside of a web page. You can have the entire sort of live database there running locally. We have built so far a React wrapper around that just triggers React to automatically re-render and kind of understands what React does. That code is on our GitHub repository. It's open source. The code in total, I think, is 600 lines of JavaScript. And it's just a wrapper around React that is interacting directly with the JavaScript version of Fluree. We do intend to and would like to, and anyone in the community can easily look at the pattern that we put in our React wrapper and do one for Angular and do one for Vue. So I anticipate we'll actually have those, or perhaps someone in the community will end up doing those. And I see now we're about a minute over, so I will stop there, and I am happy to address, at least for those I have their emails, some of the remaining questions that we have. Really appreciate everyone joining us today. Would love it if you went to our website, and if you wanted to play around with Fluree, there's a lot of great ways to do that, to get familiar with some of these concepts. So thanks everyone. Appreciate you giving me your time today. Bye.